This is the video for Module 14, Section 4.2, about solving systems of linear equations by substitution. In the last section, we talked about solving systems like this by using graphing. This section and the next section will talk about two other methods that we can use where we're actually using algebra to solve the systems. This first one is called the substitution method. And first we're going to go through the steps and then we'll look at some examples. Step one for this method is to choose one of the equations and solve it for one of the variables. Then step two is that we use one side of the solved equation from step one and substitute the expression that we came up with into the other equation. Step three is to solve for one of the variables. Step four is to take the value that we found in step three for one of the variables, substitute it into one of the equations, and use that to solve for the other variable. Here's an example of a system, and we're going to solve it using the substitution method. So step one in this method was to take one of the equations and solve it for one of the variables. If you look at this first equation, it's actually already solved for x. And when we're solving systems, we want to use the easiest method possible. So if we're using substitution and we already have an equation that's already solved for one of the variables, we're going to use that to our advantage. So for step one, this is actually already done for us. We have that first equation solved for x. Now for step two, we're going to take the expression that's on the right side of this equation. So since we have it solved for x, we're going to take the expression that involves y and substitute it into the other equation. So we're going to substitute the expression y minus 2 in place of x in our other equation. So in the equation x plus y is equal to 6. So in place of the x there, we're going to substitute this whole expression, y minus 2. Now our third step is to take what we just did in step 2 and just solve this resulting equation for the variable that we have left. So we'll take this equation and we're going to solve it for y. But we can take the parentheses off to start with, so we have y minus 2 plus y is equal to 6. Then if we combine like terms, we have a y and a y, so that gives us 2y minus 2 is equal to 6. We can add 2 to both sides. That gives us 2y is equal to 8. And then we can divide both sides by 2. So we end up with y is equal to 4. So we've completed step 3. Step 4 is that we're going to use the value. So we're going to use the value y equals 4 in one of the equations and solve for x. Since we've already got a value for y, the one that we need a value for now is x. So that's how we know here that we're going to be solving for x. Now you can put the y equals 4 into either one of the two equations that we started with, but when you're doing substitution, always what you're doing in step 1 is solving one of the equations for one of the variables. Since you already have that one solved, the quickest way to do step 4 is to use that form of the equation. So we're going to use our equation from step 1, that we had solved for x, which is x is equal to y minus 2, and we're going to substitute the 4 there in place of the y. And again, you don't have to do it this way, but this is the quickest and easiest way to solve this. So we end up with x is equal to 4 minus 2, which is 2. Now we have a solution for our system because we have a value for both x and y. That would give us an ordered pair. And remember, just like in the last section when we were solving these systems by graphing, our solution is going to be an ordered pair. Now, let's check this. And remember, to check to see if this is a solution of the system, we need to substitute those values back into both of our two equations. So the first equation we had was x equals y minus 2. If we substitute 2 for x and 4 for y, then we have 2 is equal to 4 minus 2, and that's a true statement. Now in our other equation, we had x plus y is equal to 6. Again, we're substituting 2 for x and 4 for y. If we add 2 and 4, we get 6. So that's also a true statement. So that means that this checks, and 2, 4 is our solution. Let's do some more examples. For this first example, in step 1, we want to solve one of the two equations for one of the variables. We want to do this the easiest way possible. So notice in this first equation, we just have an x here. That means it would be very easy to solve this first equation for x, because all we would have to do would be to subtract the 6y from both sides. So we're going to take this one and just subtract 6y from both sides. And there's our equation solved for x. Now our second step is to take the expression that we have here and substitute it into the other equation in place of the x. So for writing out our other equation, where the x is, we're going to put a big set of parentheses so that we can substitute in our whole expression. Right here, we're going to replace that with the expression 2 minus 6y. Now step 3 is to take that and solve it for whatever variable is there. In this case, we have a y there. So the first thing we're going to do in solving this is distribute the 4. We have 4 times 2 minus 4 times 6y plus 5y is equal to negative 11. That gives us 8 minus 24y plus 5y is equal to negative 11. If we combine our like terms, negative 24y plus 5y gives us negative 19y. And then if we subtract 8 from both sides, that gives us negative 19y is equal to negative 19. If we divide both sides by negative 19, that's going to give us y is equal to 1. Now for step 4, we're going to take that value that we just found, the y equals 1, and substitute it into one of our two equations. And again, we can use the equation from step 1, which was x equals 2 minus 6y. So we're actually going back to this equation that we have at the end of step 1 because we had already solved it for x. And then we're substituting in 1 for y. That gives us 2 minus 6, so our x is equal to negative 4. So now we have the ordered pair negative 4, 1 as a solution. Again, if we want to check that, we'd go back to our two equations and substitute those values in. From our first equation, we'd have negative 4 plus 6 times 1 equals 2. Notice that here to do this checking, I'm going back to our original two equations. So we have negative 4 plus 6 is equal to 2. That would give us 2 is equal to 2, which is true. Then our second equation, we have 4 times negative 4 plus 5 times 1 is equal to negative 11. That gives us negative 16 plus 5. And that's also going to give us a true statement. So that means for this one that our solution is the ordered pair negative 4, 1. Okay, let's do our second example. If we look at our two equations here, if you notice in this first one we have a y that doesn't have a coefficient. It actually has 1 as a coefficient, but that would be a very easy one to solve for. So if we take this one and solve it for y, that means all we have to do is subtract 4x from both sides. That gives us y equals 11 minus 4x. Now for step 2, we're taking our other equation, and this time we're going to substitute this expression into our other equation in place of y. So our second equation was 12x plus 3 times y. So we're putting big parentheses there so that we can substitute in our expression. Now for step 3, we're going to take that equation and solve it for x, since that's the variable we have left. Let's start by distributing our 3. So we have 3 times 11 minus 3 times 4x. That gives us 33 minus 12x. If we combine like terms, we have a 12x and a negative 12x, so those two actually cancel each other out. And that means all we have left on our left side is 33, and all we have on our right side is 33. Now what we have here is a statement that doesn't have any variables left, so we can't really solve it for x because we've eliminated the x's, but we know that this is always going to be a true statement, because 33 always has to equal 33. So this is always going to be true no matter what x is. What that tells us is that we could put in an infinite number of values for x and always get this to be a true statement. And that tells us that we have dependent equations. If you remember from the last section, dependent equations mean that both equations represent the same line. And that means that there are an infinite number of solutions. So for this problem, our answer is not an ordered pair, but we would just say we have an infinite number of solutions. Anything that would solve either of these two equations would solve both of them. Here are some more examples. For this first example, if we look at our two equations, in this first one again we have a y that doesn't have a coefficient with it. So that would be the easiest thing to solve for. So we're going to take this one and solve for y. We're going to be adding 4x to both sides. Now for step 2, we're going to be taking this expression and substituting it into the other equation in place of the y. So in place of the y that went there, we're going to be substituting negative 1 plus 4x. For step 3, we're taking that equation we got in step 2 and just solving it for x in this case, since that's the variable we have. So we're going to distribute the 6. So we have 6 times negative 1 plus 6 times 4x. That gives us negative 3x minus 6 plus 24x is equal to negative 6. If we combine like terms, we end up with a 21x minus 6 is equal to negative 6. Now if we add 6 to both sides, we end up with 21x is equal to 0. Now we're still trying to solve for x, so we're going to divide both sides by 21. And remember, if you have a fraction with 0 on the top, then it just has a value of 0. We've got our value for x. Now for step 4, we're going to use that to find the value for y. And again, let's go back to the equation that we had in step 1 that we had solved for y. So we're going to use x equals 0 in the equation y is equal to negative 1 plus 4x. We're just putting the 0 in place of x. That gives us negative 1. 4 times 0 is 0, so we just end up with a value of negative 1. This would mean that our ordered pair that we think is the solution is that x is equal to 0 and y is equal to negative 1. And let's check this. Remember, for the check, it's best to go back to the original two equations that you had. So we had negative 4x, that's going to be negative 4 times 0, plus y, which is negative 1, is equal to negative 1. Well, anything times 0 is 0, so we've got 0 plus negative 1 equals negative 1. That's going to give us a true statement. With our other equation, we have negative 3 times 0 plus 6 times negative 1 is equal to negative 6. And negative 3 times 0 is 0. 6 times negative 1 is negative 6. So we end up with negative 6 is equal to negative 6. So that's a true statement. And that means that the solution we came up with is a good one. Solution for a system of equations is going to be an ordered pair. So this is our solution. Okay, let's do another example. Now here's a problem where all 4 of our variable terms have coefficients. So we don't have an easy solution like we have in the other examples. So here really you could choose any of these variable terms and use it to solve. The only thing is I would probably pick one with a smaller coefficient just because that makes your fractions a little bit easier to deal with. So let's pick this one as what we're going to solve for. Okay, so if we're solving this equation for x, that means that we're going to subtract 20y from both sides. So we have 5x is equal to negative 20y. Then we're dividing both sides by 5. That gives us x is equal to negative 4y. So we've got that one solved for x. Then step 2 for this one is that we're going to take this expression that we got from solving for x and substitute it into the other equation. Since we chose our second equation for step 1, we're going to use our first equation for step 2. And since we had solved this for x, that means we're substituting in for x. So where the x was, we're putting a big set of parentheses. And we're going to substitute in negative 4y. Step 3 is just to solve this for the variable we have left, which is y. So if we multiply the 6 and the negative 4y, that gives us negative 24y. And then we have plus 24y is equal to negative 10. Now on the left side, if we combine like terms, these two actually cancel each other out because they're opposites of each other. So we end up with a 0 over there. And now we have 0 is equal to negative 10. We don't have any variables left, so this looks a little bit like the previous example we did, except that 0 cannot equal negative 10. So this statement is always false. That means there's no value of x and y that we could put in to here to make this true. And that tells us that our system has no solution. When we were graphing these in the last section, that means that these two lines would have been parallel, so that there's no intersection point.